So let's talk about written language processing. And really what I mean by that is the field of natural language processing, or NLP. Humans communicate in both written and spoken language, of course. We write documents, we write emails, we talk to each other. It's very natural for us. So around us in the world, there are all forms of documents and recordings. And the field of natural language processing developed a set of methods to help us process these kinds of data, whether to retrieve information, understand, summarize, translate, you name it, in a form that we can use for ourselves and computers can process as well. As you can imagine, there's many different kinds of business applications for this kind of technology, ranging from medicine, finance, law, personal use for entertainment or information retrieval, all sorts of things. One thing I would say is NLP, the field, has undergone a massive change just over the last decade, as deep learning methods have completely become dominant in all the different kinds of techniques that are being used. NLP transitioned to probabilistic models in the late 1980s, early 1990s, as they borrowed methods from speech recognition and then went on to grow their own probabilistic methods. But the deep learning with these neural network models has completely changed things. So I want to spend some time talking about that. And in particular, text in the form of characters, words, or sentences, and even documents are no longer represented as symbols, but they are mapped to what's known as embedding vectors, which are learned by neural network models and that can be used for specific NLP tasks. So I want to spend a few minutes talking about the notion of embedding vectors. It's hard to believe, but the first embedding vector representation, called word-to-vec, came out in 2013. And since then, many different alternatives have emerged, but the word-to-vec sort of revolutionized the way that NLP tasks represent words, and so it's worth spending a few minutes talking about. One of the nice things about the word-to-vec algorithm is it's based on a kind of unsupervised training. All you needed to train up these vectors was large quantities of words in documents, and those are readily available on the internet these days. The model was based on the notion of having a window of a word and neighboring words in its immediate context, and you could vary the size of the window depending on how much data you would have. And you could train up a model where you would give it the neighboring words as input, and the model would have to predict the particular word, or do the opposite and give it the particular word and have the model try to predict the neighboring words. And you would go through these documents showing it millions of examples of the word to predict the neighboring words, and you would iterate to try and maximize the probability of predicting the neighboring words. And when you were done with this training, you could use a hidden layer in the model as the embedding vector representation for the word. So you would input the word and you would use the values of that hidden layer as your vector representation for that word. And when you did that, you could build up effectively a semantic dictionary where for all of the words in your vocabulary, you could represent each word by its corresponding vector representation. And then you could use that vector representation for subsequent specific NLP tasks. Use it as an input. One of the nice properties of this embedding vector representation is that it had a geometric interpretation. If you look in this high-dimensional space, this projection, which was on the order of hundreds of dimensions typically, what we found was that words that were semantically similar tended to occur in similar regions of this space. So for example, words like boy and girl and man and woman would occur in a similar point in the space, or different animals like tigers and lions would be another point in the space, or geographic terms like water and ocean would be in another region of the space. So it was kind of nice to see that words that sort of had similar meanings and would be used in similar ways would occur in similar regions in the space. The other thing that was nice about these embedding representations is that transformations that you could make between one word and another would often translate. So for example, if you took the difference between girl and queen, it would correspond roughly to the difference between boy and king, and things like that. And so it was a nice way to interpret what was going on. Maybe you have a social forum where people are asking questions and you want to see if the existing set of answers are relevant to that question. That's called community question answering. In that kind of scenario, you have your question input that you might want to summarize in terms of a sequence of words and then translate that into an embedding vector representation. And you have an answer that you might represent as a document that you also want to embed in the vector representation. And then on top of that, you can train a model to say, this answer is a good one for this particular query, or this answer is not a good one for this particular query. And eventually you will learn a task-specific sort of joint attention to learn where to pay attention to the important information in the query and where in the answer is the relevant information that makes that answer the right one for that particular query. So I have several use case scenarios for this type of thing, and let's talk about them now. So in community question answering, you'll often get a variety of documents. There are forums on so many different topics these days, and that's what makes it challenging. But say, for example, you have somebody who's visiting a country and they want to know if on their visa they can get a driver's license, and so they post a question, and then you get a bunch of people answering the question. Some of them, of course, as we all know, they're very good answers. They're very on target and they give the information that you want. Some of the answers are like completely irrelevant. I can get you a job earning $10 an hour doing something strange, or somebody gives incorrect information. And so this is a task that we can train up machine learning models to try and judge these answers. Given the question, is this a good answer? Is this a bad answer? Is this an irrelevant answer? And we represent all of this information with embedding vectors. And again, one of the nice things about this task is it automatically learns words in the task that are semantically related to each other without having to explicitly enumerate all the things that are similar. That's the way things used to be done in the past, and that heuristic is very time-consuming and error-prone. So in this illustration I have here, we have all the words that sort of are similar to the word yes, all the words that are similar to the word no, and all the words that are similar to the word maybe, and you can see lots of good examples there. Another thing that you can do is you can actually visualize where in the question is the relevant information to help you select the appropriate answer. So for example, if somebody says a question that says, hi, I'm going to be visiting for a couple days and I'd like to go snorkeling and I have no idea where I'm supposed to go. Does anybody have some good advice? Well, really the important aspect of that question, you should pay attention to where they're saying, I'd like to go snorkeling. And that can help you sift through all the answers that are in your forum and find ones that are relevant where people talk about where to go snorkeling. Likewise, someone might say, oh yeah, I'm new in town. Are there any good places to visit? I'm only here for a couple of days. So again, the keywords there are good places to visit, and you can go through your answers and find some possibilities for the user. So there's lots of examples of where you could apply this to many kinds of forums, and this is just one particular case. I want to give another example of how we use word embeddings these days, and this is in the general problem of fact-checking. This is something that's become very popular recently, both in the news media, reporters, but also people doing NLP research trying to automate some of these processes to be of assistance. The general problem of fact-checking is very complex. There are many different subcomponents, and I'm not going to talk about all of them here. I'm only going to give a couple of sub-examples. But basically, if you have a document that comes in, you might want to try and identify some particular claims in the document that might need to be fact-checked. Then you can go and try and find some evidence from sources in the world like Wikipedia or reliable news sources. And then you might want to check the claim versus these news sources and see what the stance of that particular article is relative to the claim. Does it agree with the claim? Does it disagree with the claim? Or is it actually not that? Is it just discussing the topic and doesn't really take a stance? So let me talk about claim identification. And I should mention that these days there's lots and lots of data that are becoming available, and in fact that all of these NLP tasks and speech tasks, any machine learning task related to language rely crucially on large quantities of data, and of course they take a lot of computation to train. I'm sort of ignoring all that aspect of it, but it can be done. So for the topic of claim identification, there are lots of data becoming available, and one example, for example, is all the political debates that were transcribed, and the reporters busily went off saying, well, here's a claim, is it true or not? And this is actually a gold mine for trying to train up models to do similar kinds of things. What I want to do now is move on to talk about speech and spoken language processing, so that's the second part of my talk. It used to be I had to explain to people why speech was a useful modality that humans might like to talk to their computers. We sort of crossed that point in our society. Starting in 2011 when Siri came out, suddenly I found everybody knew what speech recognition was, or more and more people. And nowadays with Amazon Alexa and OK Google and Cortana from Microsoft, and then all the movies, science fiction movies, talk about people talking to their robots or falling in love with their conversational agents, or you name it. It's all over the place. And it's not surprising to me. You know, we all speak. Speech is so natural for us. It's easy. We can talk when our hands are busy, our eyes are busy. It's easy for us to express ourselves. And of course, we want to talk to our machines everywhere, 24/7, whether we're at home looking for movies or cooking instructions or setting timers, or we're in traffic trying to find a better way, or we're at work, you name it. The only thing I would say is that speech is much more than speech recognition, because really it's a whole loop that involves a computer. In addition to recognizing what words you're saying, the machine needs to understand the semantics of what you mean in the larger context of what's going on. And then it has to figure out what its action is going to be, and call that dialogue management. And it has to do something for you, show you something, get information, maybe say something to you as well. One of the things I love about speech is that it's a signal, and it contains so many different kinds of information. First of all, we're all different. Every person on the planet, the physics of their vocal tract is slightly different. So the speech we all produce is slightly different. The resonances we produce are all slightly different. So there's information about the talker in the speech signal. There's information about the health of the talker in the signal. Do you have a cold? And you can get into other things. We're starting to look at things like cognitive impairment and depression just from the way people talk. There's the emotional aspect. Are they happy? Are they sad? Are they angry? Of course, there's the language. There's the linguistic information. I'm speaking English. What are the words that I'm using? What dialect do I have? What is my style? Am I reading speech? Is it formal or is it conversational? I'm chatting with friends. And lastly, all the environmental aspect gets picked up in the acoustic recording as well, especially when the microphone is far away from me, like it would be for Alexa or something like that. So there's a whole host of underlying technologies that you can get into that have reached a point where it could be useful for people today. And let me just give you a quick rundown here, but things like acoustic scene analysis, if you want to analyze the general sounds that are being made. Of course, detecting speech, this is something that these distant devices, they're always listening, and they're trying to detect when you're talking to them specifically, like Alexa or OK Google. I'll come back to that later. Identifying who's talking, speaker identification. If you have a meeting where multiple people are talking, it's called speaker diarization. How many people are talking and who's talking when? That can be a useful way to summarize a recording of a meeting. You can analyze how they're talking, so things like sentiment analysis or prosodic analysis. You can get at the meaning, what is meant, disciplines like language understanding, dialogue management that I mentioned, and then the output side as well. All of these are different aspects of processing the speech signal that people are working on. And there's so many different ways they could be applied to real-world problems. Obviously, human-computer interaction is a good use case, but also processing content, YouTube videos or other recordings that you have. It can be useful for language learning, helping people learn new languages. It can be used in health scenarios. There's so many different things. Let me talk about a couple of them now in the time that I have. And first, since we've been talking about NLP, let me talk about speech understanding in the context of devices like Siri and things like that. These are instances of what I call spoken dialogue systems, where somebody's saying something that's usually task-specific. What's the weather going to be like this weekend? You know, we did that in the late 1990s, and now everybody can do it on their devices. Or maybe I would like to fly from Boston to Toronto on Monday. It's typically a much more focused type of input than you would get in the free-form text-based processing that I talked about previously. But still, people are using deep learning models to help with the understanding. In the case of these types of queries like a flight, you might want to detect the intent. That in this case the person is trying to book a flight. And then you would try to identify what the values of particular semantic slots are, like what's the source city, what's the destination city, when do they want to travel, what date would they travel on. And then you can look up information in a database and show them some flights, for example. So the third part of this module is talking about multimodal language processing, where we combine speech or text with a parallel modality like visual input or gesture or something like that. First, I'm going to talk about the notion of asynchronous modalities for interaction. One of the nice things about asynchronous multimodal interaction is if you have an interface like a speech interface that you're talking to, sometimes doing something different like making a gesture is a more natural thing for people to do rather than trying to describe something verbally like a region on a map. For example, I'm looking for restaurants in this area rather than trying to describe the location precisely. So what I've found with these types of multimodal interfaces is that they're more flexible because the user can select the modality that they want to do in the particular context in which they're in. They also can be more efficient, because language combined with gestures can simplify the overall interaction, and in a way they're more natural for people. The other thing that's nice about these types of multimodal interfaces is that if you can provide visual feedback to the user, one of the things that you can do is convey the system state of understanding, even if you're talking to the user as well about their answer. The visual information performs a kind of visual feedback, a parallel back channel to the user, which can make the overall conversation flow more efficiently. And let me give you an example of audio-visual combination. Now, this is not an exact match, but we've been doing some work on video snippet retrieval. These days, YouTube and the like contain millions of videos, often with useful information, and it'd be nice to find videos that are relevant to a particular question that you have, and maybe find a particular snippet in the video that is the exact answer that what you're looking for, rather than having to wade through the entire video. So for example, if you're in your car and there's some button you don't know how it works, like in this question, what does the auto function for the air conditioner do? What you'd really like, car companies make all sorts of how-to videos about the functionality about their vehicles, but what you'd really like to do is find the sub-snippet of the video where they're talking specifically about the auto function on the dial for your air conditioner. And you can do this type of thing. It's similar to the community question answering that I talked about before, where you have a query and you're trying to find a match with a particular piece of a document. Potentially you could incorporate visual information as well, however. Now, in other scenarios for multimodal processing, you have synchronization between the two modes, and the most obvious one is audio-visual. And you can imagine that for a variety of different things. First of all, If you're trying to locate where the person is talking, you can use microphone arrays, but you can also use cameras to help locate who's talking. I talked about speaker ID. Well, you can complement that with face ID to figure out who the person is. You can combine speech recognition with lip reading capability to improve, get more robust speech recognition. We all do this when we're in extremely noisy environments talking to somebody. We pay a lot of attention to their face when we're listening to them. And finally, what we call paralinguistic, things that don't have to do with a linguistic message like the emotion or some other state of the user. You can get information both from how they're talking, but also how they look. And combined together, all of these components will give you more robust capabilities than you could on their own.